From the crayons to the blueprint paper to the markers, except I did buy some new markers. So the aliens, you can color those in a little bit if you want. So again, the two bonds on the O here, what would those be? That'd be H2O, right? So 1, 2, that'd be H2O. Now underneath N, this is where our first great discovery came. Phosphorus, markers, since we bought these. Phosphorus has 5 bonds that it can do, or 3, but so see that? 5 bonds. Let's just use those, even though you never find this because it's too big. But 2, 3, 4, 5. So this is underneath underneath nitrogen. But then when we looked underneath oxygen, sulfur can have 6 bonds. So we came up with the old Star of David here. 6 bonds on that. 1, 2, 3, 4, 5, 6 bonds on sulfur. So isn't that neat how the star comes into play here? 5-pointed star for the phosphorus, 6 for the sulfur. This is fun stuff. And we're still working on it, but I think green has to be it because it's in the same family as the oxygen. So there's sulfur, phosphorus. Now what we did for helium, we even found we can do it as a sun. Just since we're doing shapes here, huh? So helium is just the sun. And our sun is actually a yellow. Yellowish orange our sun is. And don't let them tell you our sun is a typical star, because it is not by a long shot. For one thing, it's an independent. Everybody else has pairs, binary, trinaries, 4, 5, 6 stars all in orbit. Ours is all by itself. So to learn the Schroeder diamond technique here, just simply learn what the valence is. Hydrogen is 1. Calcium, magnesium, barium, it's at 2. 120-degree triangle is for the 3s. The diamond, carbon diamond, is 4. Now these do different characters. So even nitrogen has 3 bonds. The phosphorus could do that, but we give it a 5-pointed star here. Oxygen, 2 bonds, 2 lone pairs. Sulfur could do the same thing, but it gets the equivalent of 6 bonds around here. Then what we do for the halogens is a square. So like fluorine, fluorine only gets 1. And we're still determining what to do about this lone pair thing, because we put aliens on the corner, I guess. So this is HF, this would be hydrofluoric acid, right? So now when you do chlorine underneath, still do it as a box. And what you can get is the equivalent for each lone pair here can be an O. So there's an oxygen. The alien bonds to another double bonded oxygen. Alien here, another bonded oxygen, so we should make these bigger, I guess. That's the O. And what it still has is the single there. So what you're able to get now is a single bonded O. So that would be hydrochloric acid. This would be HClO4. That's the biggest molecule you'd ever have to draw the Lewis structure for. So we color these halogens in, bringing kind of a purplish color. Like a little purple, so halogens are purple. Fluorine, see, this is HF. It'd be hydrofluoric acid. Because the atom is smaller, the lone pairs aren't able to bond like the bigger atom chlorine does. So everything underneath chlorine will do the same thing, have all these different possibilities. So you've got bromine and iodine will do the same molecules as that. So that's the premise here of the Schroeder diamonds. Look, we found all these colors in the dumpster. Color the phosphorus orange. You can draw anything. What you do now is you find a chemical structure in a book, and then you draw it yourself. Sulfur's yellow. In mixed media, use colored pencils, use markers, use crayons. So sulfur, phosphorus, aluminum, 2, 1. 1, 2, 3, 4, 5 is 3 bonds, 6 is 2 bonds. Your halogens. One bond on the fluorine. When you get to the chlorine, bromine, or iodine, you can get all kinds of different things going on. Just like sulfur. Right? You start putting oxygens, you got 6 different ways that you can bond O2s. And so there you go. That's how to use the shapes.